This podcast involves us practicing our interpretation of multiple regression estimations. We focus on multiple regression because this is the far more common usage of regression modeling in social science. Rarely, in fact, do we encounter unicausal hypotheses in the social sciences, meaning that one independent variable explains all of the variation in the dependent variable. And this one independent variable almost miraculously meets the other standards of causality, such as the variation in the independent variable takes place before we witness the variation in the dependent variable taking place, and that there is a theoretically plausible reason that the independent variable should affect the dependent variable. Instead, we almost always find complex, multi-causal explanatory factors for any dependent variable that is of interest to us. Since that is true, we must train our efforts on correctly interpreting multiple regression output in order to account for these multi-causal effects. Here's a conceptual model that we will interpret using multiple regression output. The dependent variable is the feeling thermometer for Donald Trump in 2016, as derived from survey respondents to the American National Election Study, where the range of values of this interval level variable have a range from 0, or a very negative feeling, to 100, or a very positive feeling toward Trump. The independent variables are the income range of the respondent, the race of the respondent, the gender of the respondent, and the educational attainment of the respondent. So this is a socioeconomic explanation of support for Trump. If we can make the plausible inference that positive feelings on the thermometer scale toward Trump indicate support toward Trump in the 2016 presidential elections. Since we have 4 independent variables, we have 4 slope coefficients to consider. Let's start with the first slope coefficient, that of the income range of the respondent. We know from the measurement of the variable that there are categories into which the respondent falls. Each unit increase in the income category results in anywhere between a $1,250 to $5,000 to $10,000 increase in income. Those are substantial increases. We can see that as income increases by one category, there is a small decrease in the Trump feeling thermometer of about 1/10 of a point. However, we can interpret the significance of the slope coefficient with the t-statistic of negative 1.24. And we put that in absolute terms in the parameter estimates in the slide, so that turns into a positive number, or positive 1.24. The t-statistic fails to reach statistical significance, as it fails the rule of 2 for statistically significant slope coefficients. Thus, the respondent's income has no significant impact on variation in the Trump feeling thermometer. We can quickly note, if we look at the t-ratios, in parentheses, that the other independent variables are statistically significant in explaining variation in the Trump feeling thermometer. They're certainly impressive in the size of their t-statistics, from 5.0 in absolute terms to 17.49. Thus, a black respondent, all other things being equal, shows a 32.3 decline in feeling thermometer scores for Trump. Females show a 5.9 decline in the Trump feeling thermometer. Lastly, those who shift from some high school or a high school degree to some college work completed, and from some college completed to having completed a bachelor's degree, and from a bachelor's degree to a post-baccalaureate professional or doctoral degree, will show a 7.5 decline in the Trump feeling thermometer score as respondents go down each part of the educational attainment scale. The model thus appears to demonstrate some impressive independent impacts in explaining variation in the Trump feeling thermometer. What about the strength of the model as a whole? We look to the R-squared statistic, in this instance the adjusted R-squared statistic, since we have multiple independent variables in our model. The adjusted R-squared, in fact, is the more accurate measure of the model performance as opposed to R-squared. Since we're looking at survey data from the American National Election Study, R-squared will generally be lower because the respondents are limited in the categories in which they can provide their responses. Having said that, the adjusted R-squared is 0.13, meaning that 13% of the variation in the Trump feeling thermometer is explained by these 4 independent variables. The standard error of estimate is 32.87, which means that the standard deviation of the actual value of the dependent variable, the Trump feeling thermometer, from the predicted value of the Trump feeling thermometer using the slope coefficients from the 4 independent variables is different by about 33 points. So the model itself is relatively inaccurate in capturing the Trump feeling thermometer score. And I should add that the total number of cases is high because this is a major survey, the American National Election Study, more than 3,000 respondents. In this multiple regression analysis, we can work our way through the regression assumptions. The first assumption is that there is no specification error, and it has 3 sub-assumptions: that the independent variables and the dependent variable have a linear relationship, that there are no relevant independent variables that are excluded from the model, and that there are no irrelevant independent variables included in the model. So let's look at these one by one. I don't report this here, but in fact, what we can do is we can regress each independent variable on the dependent variable and look at the R-squared value. If the R-squared value is high, then we can determine that the independent variable has a relatively linear relationship with the dependent variable, because the regression line is capturing a lot of the variation explained. However, when I ran these independent variables separately, each regressed on the dependent variable, the R-squared values were very low, none really higher than 0.15, which is a very low value for R-squared. So that tells us that the linearity that is in this particular model between the dependent variable and the independent variables is slight at best. So let's move to the no relevant independent variables excluded sub-assumption. To look at this particular sub-assumption, we look at the model R-squared, or the adjusted R-squared. To review, the adjusted R-squared of 0.13 tells us that there is much more variation to capture in the dependent variable, the Trump feeling thermometer. In other words, 87% of the variation is unexplained by the 4 independent variables in this model. Thus, we're in relatively major violation of this regression sub-assumption. The obvious solution is to find more independent variables that have a significant relationship in explaining the dependent variable's variation. Now, the next sub-assumption of no irrelevant independent variables included in the model, we can assess that by looking at the t-statistics for each of the slope coefficients. And we can see for the I independent variable, the income independent variable, that's the only one that is irrelevant or insignificant in explaining variation in the Trump feeling thermometer. In other words, as far as that sub-assumption goes, we are not in major violation of it. The next one is no measurement error. And in order to assess this particular assumption, we need to know how the data are gathered. We can't really tell much information about this assumption by just looking at the parameter estimates, the slope coefficients, the t-statistics, and the r-squared. We can't tell much as far as measurement error goes. So what we really need is we need a code book that'll tell us how the data are gathered. Since we don't have such a code book in front of us, we will instead note that the American National Election Study is a reputable survey, having been given for decades, and that we expect there to be no significant error in the measurement of the variables. So some of this involves the reputation of the data set that we're looking at, or the reputation of the survey firm that we are considering. The next assumptions involve the error term. So the first one of these, that the error term has zero mean, we really do not need to concern ourselves with that one, because that relates to whether or not the y-intercept is biased. And that is not of as much importance to us as the significance of the other independent variable and the slope coefficients that are in the model. So we don't really concern ourselves with the error term having zero mean. The next one, the error term is homoscedastic, is relatively important. When we observe the residual plot, residuals are the observed value of the dependent variable minus the predicted value of the dependent variable from the regression model. We should see that there is no particular pattern to the residuals, that it should be a relatively flat horizontal line across the page. But in fact, we see that there is a consistent pattern to the residuals, or the errors, in this residual plot. In fact, if we go from lower to higher predicted values for the dependent variable, we see that the errors in the predictions switch from positive errors, meaning that the model underpredicts the value of the dependent variable, to negative residuals, where that the model overpredicts the dependent variable. And this is relatively serious because this indicates that our model is biased in its predictions. And so we would need to ideally correct for this type of error in the regression assumption. In fact, the error is heteroscedastic, non-constant error variance, as opposed to homoscedastic, or constant error variance. The next error term assumption involves something called autocorrelation. And this involves consecutive error terms in the data set being correlated with each other or associated with each other. Since our data set is cross-sectional, we're taking at only one time point in 2016, we assume that the errors in the respondents, in the consecutive respondents in the data set, are not connected to one another. There's low probability that we would have autocorrelation in a cross-sectional data set. In fact, it's much more likely that we would have autocorrelation in a time series data set when over time there is a relative consistency to the data points and thus a consistency to the errors in predicting those data points year after year after year. So in time series data sets, there is the expectation that you will violate the autocorrelation assumption, but not in a cross-sectional data set. The next error term subassumption to look at is one where the error term is uncorrelated with the independent variables. This is relatively likely in our model. For instance, we consider that r-squared value, if we go back a slide, that adjusted r-squared value of 0.13 tells us that 87% of the variation in the Trump feeling thermometer is unexplained in the model. This means that there are quite a lot of independent variables that could explain variation in the dependent variable that are not in the model. Since the error term is a collection of the independent variables that are not in the model, we thus have an error term that is highly correlated with the independent variables. The regression assumption is likely to be violated in this case. And what are the consequences of violating this particular assumption? It means we're not as confident that our model estimates are indeed the best linear unbiased estimates that we would hope for in multiple regression analysis. We cannot be certain that the estimates from our sample thus reflect the true population estimates. Should we simply not believe those estimates then? Well, that answer is not so simple. It is possible to correct our estimates, for instance. If we added more independent variables to our model, our R-squared statistic would increase, and thus we would be able to explain more variation in the dependent variable. So that's one way to address that particular subassumption. But in this particular model, we just have these 4 independent variables. The final regression assumption is that the error term is normally distributed. If the sample size is large enough, then we can invoke the central limit theorem, which means that the sampling distribution will look normal. Now, if we go back, we'll see that the total number of cases in our regression model is 3,233. That's well above the central limit theorem when that takes effect at n equals 30. So we can easily invoke the central limit theorem and say that the error term is normally distributed. So we have interpreted the regression assumptions for this model. And we can say that most of the assumptions have been met, and we've discussed how to address potentially some of these results. So, good work for making your way through this particular podcast, and hope you have a nice, peaceful day. Thank you.